Usually when we think of a technological revolution, we picture software, right?
Yeah, exactly. We imagine code, something totally weightless and invisible just happening in a server rack or floating out in the cloud somewhere.
Right. You type a prompt into an interface, and a fully formed essay or a compiled piece of software or even a complex financial model just kind of materializes on your screen.
And we have spent decades intentionally abstracting away the physical reality of all that computing. The consumer experience is designed to feel, completely frictionless. It hides the massive industrial base that actually powers the whole thing.
But looking at the reality of the year 2026, that invisible cloud is rapidly becoming a story of concrete, copper wiring, nuclear fuel, and literal rockets. So welcome to the deep dive. Today our mission is to map the tectonic shifts defining this year.
And we are looking at a massive stack of sources for this.
We really are. We've got venture market reports from Sequoia Capital and SeedScope, infrastructure projections from Avid Solutions, data on space commercialization, and some fascinating thought leadership from A16s on human longevity.
And the overarching theme here is that we are definitively moving out of the purely digital hype phase of the early 2020s and into the applied phase.
Yeah, and that transition is incredibly physical.
It really is. Today we're exploring how the insatiable energy hunger of artificial intelligence is forcing a literal revival in nuclear power. We're looking at how a new generation of AI-native teenagers is redefining what a startup even looks like, how advanced manufacturing is moving into low Earth orbit, and ultimately how all of this tech is converging to radically extend the human lifespan.
It's a lot to cover. But if you are an investor looking for the next big wave, or a founder planning your next pivot, or just someone insanely curious about the future, you really need to understand how these seemingly separate fields, from microgravity to microchips, are actually colliding.
They are all deeply interconnected.
Okay, let's unpack this. I want to start with the sheer scale of the AI infrastructure boom, because the numbers are just hard to wrap your head around.
They really are.
According to Avid Solutions and McKinsey, global data centers require a $6.7 trillion investment by 2030, and $5.2 trillion of that is specifically allocated just for AI-ready centers.
Which is wild. That figure represents the largest, most compressed infrastructure investment cycle in modern history. I mean, it's unprecedented.
So what's actually driving that? Like, why the sudden need for completely new centers?
Well, the catalyst for this massive deployment of capital is a fundamental shift in computing workloads. The industry is transitioning from the era of AI training to the era of AI inference.
Let's break down that distinction, because it literally changes the physical geography of where we have to build these data centers.
Exactly. So during the training phase, you are feeding trillions of data points into a model to teach it how to recognize patterns. That is a massive, concentrated effort. You can build a training facility out in the middle of a desert next to a giant solar farm because latency, the time it takes for data to travel back and forth, doesn't really matter for training.
Right, because the user isn't waiting for a response in real time.
Exactly. But inference is when that trained model is actually out in the world, analyzing new user data and generating responses.
Meaning the computing load shifts from a massive centralized batch process to billions of concurrent low-latency API calls.
Yes, and those inference workloads generate steady revenue, but they require nearly instantaneous responses, often under 10 milliseconds. And because you cannot break the laws of physics, you can't break the speed of light, computing has to physically move closer to the end user.
So it's shifting from those remote centralized hubs out to regional edge environments.
Exactly.
Wait, the economics of this build-out seem incredibly fragile, though. I mean, Sequoia Capital has officially declared 2026 the year of delays.
Yeah, that was a major takeaway.
The sources highlight that the bottleneck isn't venture capital. There is plenty of money. The bottleneck is the physical supply chain. They specifically call out the TSMC break.
Right. Taiwan Semiconductor Manufacturing Company. They essentially hold a monopoly on fabricating the world's most advanced microchips, but the bottleneck goes much deeper than just their production schedule.
Oh, definitely. It traces all the way back to the equipment they use, right? Like the EUV lithography machines made by ASML.
Yeah, and these are machines the size of a bus. They use mirrors polished to atomic precision to etch transistors the size of viruses. I mean, you can't just build a new factory overnight to make more of these.
No, it takes years and billions of dollars just to construct the clean rooms. And we are also seeing cascading delays in really basic industrial inputs, too.
Like what?
like the specialized liquid cooling units, because these high-density AI servers run so incredibly hot.
Right. The physical world simply cannot move as fast as software scales. You cannot code a copper mine or a liquid cooling tower into existence.
Which is such a great point.
And these physical friction points have actually pushed the consensus on achieving artificial general intelligence AGI out from the late 2020s and into the 2030s.
I have to question the underlying logic of this entire boom then. I mean, if construction costs for these edge data centers are rising at a 7% compound annual growth rate and power consumption is surging 165% by 2030, doesn't the physical reality of just laying copper wire and pouring concrete threaten to pop the entire software hype bubble?
If we connect this to the bigger picture, this physical constraint is exactly what forces generational innovation.
How so?
Well, AI servers alone are projected to account for 64% of all new data center power needs by the end of the decade. A single AI-focused hyperscale facility can draw as much electricity as a city of 100,000 homes.
That is just terrifying.
It is. This demand profile is fundamentally breaking our current utility grids, which means the tech industry now has to solve global energy generation just to keep its own products running.
Which brings us perfectly to how the market is desperately trying to solve this energy hunger. And the first major front is the battery race.
Right, because data centers require constant baseload power.
Exactly. They cannot afford to go offline just because the wind stops blowing or the sun goes down. The holy grail they are chasing right now is the 100-hour battery.
Which is so completely different from what we're used to. I mean, standard lithium-ion batteries are excellent for electric vehicles because they are lightweight and can release energy quickly.
But they degrade rapidly.
Yeah, and they are far too expensive for multi-day grid storage. The market needs batteries that can discharge a steady flow of electricity for 4 straight days.
And we're seeing entirely new chemical architecture step up to fill this gap. Form Energy is scaling what they call iron-air batteries. Then you have Or Energy, which just wrapped up a massive pilot program connected to the grid near Paris with the French utility EDF. And Noon Energy is operating a carbon-oxygen battery system.
The mechanism behind that iron-air battery from Form Energy is particularly elegant. It essentially harnesses the chemical process of rusting.
Wait, rusting? Like just regular rust?
Yeah, exactly. When the battery discharges electricity, it breathes in oxygen from the air and converts iron metal to rust.
Wow.
And then when it charges, the application of electrical current reverses the process, turning the rust back into iron and exhaling oxygen.
That is brilliant.
It is heavy and it's totally stationary, but iron is incredibly abundant and cheap, making the economics of 100-hour storage suddenly viable.
But here's the thing. Even with these reversible oxidation batteries backing up renewable grids, the math still doesn't close for the largest hyperscalers. The baseload requirements are just too high, so big tech is going nuclear.
They have to. The legacy grid simply cannot accommodate gigawatt-scale additions on the timeline AI requires.
Right, so we are looking at Meta placing massive capital bets on advanced nuclear startups like TerraPower and Oklo.
Yeah, the Oklo data is fascinating.
Looking at their projections, Oklo could deploy up to 1.2 gigawatts of capacity at a site in Pike County, Ohio by 2030. Based on their advanced fission designs, that could mean stacking up to 16 of their Aurora microreactors at a single campus.
But the regulatory and engineering hurdles for nuclear are notoriously high, which is what makes the strategic partnerships in this space so critical.
Yes, and there is an incredible circularity in the sources regarding this. Oklo is partnering with the Idaho National Laboratory to use an AI platform called Prometheus AI to accelerate the design and regulatory pathways of these exact nuclear reactors.
What's fascinating here is the feedback loop.
It's crazy.
The system is optimizing fuel burnup rates and navigating these complex safety simulations to design the very power source it requires to sustain its own intelligence.
AI is now so power-hungry that it's literally being used to design the nuclear reactors required to keep itself turned on. It's like a brain building its own heart.
That is a perfect analogy, and the implications for energy independence are massive. Because of these microreactors and multi-day batteries, on-site power generation for data centers is expected to jump from 13% to 38% by 2030.
Wow.
And the number of facilities running completely off-grid is projected to jump an incredible 27-fold. This is a complete restructuring of how industrial power operates.
Okay, so while the physical infrastructure fights to catch up, the software layer running on top of it is still pulling in staggering amounts of capital.
Correct.
In just the first quarter of 2026, $242 billion in venture capital poured into AI.
That is just an astronomical amount of money.
It accounts for 80% of all global VC funding. But the nature of that funding has evolved significantly, right?
Very much so. The spray and pray investing era is over. The era of funding generalist foundation models with the hope they figure out a business model later, that's ending. The new standard for reaching massive revenue scale quickly is vertical AI.
And according to reports on companies like AppScript and Ingenious NetSoft, vertical AI is building the new $0 to $1 billion revenue club.
Right, because instead of building a chatbot that tries to be a poet, a programmer, and a lawyer all at once, these companies target one highly specific, complex workflow within a single industry.
And the return on investment is immediate and measurable. For example, we are seeing AI medical scribes that deeply understand dermatology or cardiology terminology.
Right, they actively capture patient interactions and do the billing coding automatically.
Exactly, and they are charging $599 to $599 per provider per month.
Those vertical solutions command a massive valuation premium because that domain-specific training data creates a formidable defensive moat. I mean, a generalist language model is prone to hallucinations.
And in fields like medicine or corporate law, the cost of hallucination is catastrophic.
Exactly. So a vertical AI system wrapped in retrieval augmented generation, referencing a proprietary database of verified medical protocols, solves a highly painful, high liability problem.
We are also seeing this in generative engine optimization, or GEO, where startups help local businesses like plumbers and mechanics format their data so they're recommended by AI assistants, instead of relying on traditional search engine results.
Which just points to how deeply AI is becoming embedded in traditional non-tech industries.
Here's where it gets really interesting regarding consumer adoption, though. The venture firm A16s published their thesis on the startup ideas they want to fund in 2026. And one of their major concepts is the AI native university.
Ah, yes. Where human professors step back to become architects of learning, basically curating data and tuning personalized models for students.
Right. But when you read the Reddit community discussions linked in our sources, there is brutal skepticism. One user pointed out the obvious flaw. Nobody wants to pay thousands of dollars just to sit in a dorm room and talk to a chatbot.
Yeah, that's a very fair point.
Are ZCs like A16s just too disconnected from what normal consumers actually value in education?
Well, that critique cuts to the core of a recurring technological trap, which is forcing a paradigm-shifting technology into a legacy container.
Like trying to make a digital version of a physical classroom.
Exactly. VCs often try to digitize the existing world, like taking the traditional university structure and replacing the lecturer with an avatar. But the real transformation won't be an AI university. It will emerge from the demographic that has never known a world without this technology.
The AI native teens.
Yes. The Sparkinify analysis in our stack breaks down the psychology of this generation perfectly. For a teenager today, generative AI isn't an impressive novelty. It is basic, invisible infrastructure.
Much like the internet was for millennials or the smartphone was for Gen Z.
Precisely. They don't write essays from scratch. They co-write. They don't spend months prototyping code. They co-build applications over a weekend.
Because the artificial intelligence layer makes the actual execution of complex ideas incredibly cheap and nearly instantaneous. So their baseline capability is just orders of magnitude higher than previous generations.
Right. If an AI agent can generate 50 viable business plans, write the back-end code, and deploy the marketing assets in a few hours, your competitive edge is clearly no longer your ability to write code.
So what is it?
The premium shifts away from raw technical execution and toward human judgment. The critical skills for this generation are emotional intelligence, ethical reasoning, and the discerning taste to know which of those 50 generated ideas actually solves a meaningful human problem.
That makes total sense.
And furthermore, this demographic will treat embodied AI humanoid robotics like Tesla's Optimus or Figure AI models as assumed platforms.
Meaning they will design businesses operating on the assumption that intelligent machines can move, lift, and assist in physical space just as easily as software operates in the cloud. We are heading for a massive blurring of the lines between a traditional local business and a tech startup.
And that transition from writing code to utilizing autonomous physical robotics isn't just happening in local warehouses or edge data centers. The plummeting cost of automation and launch vehicles is opening up an entirely new industrial base off-planet.
Let's transition to that frontier because it represents the ultimate convergence of hardware and autonomy. The orbital economy.
It is a massive shift.
We are not talking about space tourism or satellite communications anymore. We are talking about heavy manufacturing in microgravity.
Space is rapidly becoming an extension of our terrestrial supply chain. It is perhaps the most extreme example of vertical tech solving highly specific industrial problems where Earth's physical environment is the limiting factor.
Startups are operating in ways that sound entirely fictional. I mean, Cislunar Industries is actively capturing space debris and recycling it into usable metal rods and wire directly in orbit.
Creating a literal off-Earth supply chain.
Yes. And Spaceforge is manufacturing ultra-high-quality semiconductors in microgravity, and Varda Space Industries is partnering with United Therapeutics to formulate actual pharmaceutical treatments for rare pulmonary diseases inside orbiting capsules.
The scientific foundation for manufacturing in space comes down to fluid dynamics. Here on Earth, gravity creates buoyancy-driven convection currents. Lighter, warmer fluids rise, and heavier, cooler fluids sink.
Just like boiling water.
Exactly. And this constant microscopic churning creates defects and inconsistencies when you are trying to grow uniform crystal structures or layer highly sensitive semiconductor wafers.
It's like a master chef working in a kitchen that's constantly shaking, ruining a delicate souffle.
That's a great way to look at it. In microgravity, those convection currents and sedimentation processes simply do not exist. Diffusion becomes the primary mechanism for mixing, which is incredibly slow and stable.
Meaning molecules can assemble themselves into perfect, highly ordered lattices.
Right. And for pharmaceuticals, these perfectly ordered, space-grown crystal structures literally alter the drug's properties. It can lead to vastly improved bioavailability, meaning the therapeutic compound dissolves and is absorbed by the human body much more consistently.
And it can also transform a drug that normally requires an IV drip into a stable subcutaneous injection while significantly enhancing its shelf life.
Yes, the science is incredibly elegant.
The science is elegant, but the logistics seem impossibly complex. I mean, looking at the satellite propulsion market data, the sector is booming to $43.9 billion by 2035. Companies are struggling with supply chain issues, forcing them to transition from xenon gas to alternative electric thrusters.
Using krypton or solid iodine, yeah.
Right. Add in the severe regulatory red tape of international export laws, launch insurance, and the sheer violence of atmospheric reentry. I have to question, is the return on investment for a space manufactured drug really high enough to justify strapping it to a rocket and dropping it back to Earth?
This raises an important question about how we view manufacturing economics. The metric here is value versus volume.
Okay, what do you mean by that?
You are never going to manufacture standard aspirin in low Earth orbit. The economics only work for highly specific life-saving therapeutics, where terrestrial physics physically prevents the molecular bond required for the treatment. It is a high-value, low-volume paradigm.
Oh, I see.
As autonomous robotic labs mature and reentry systems become standardized, leveraging the vacuum and microgravity of orbit becomes a totally viable strategy for specialized biomedicine.
And what connects this orbital pharmaceutical research to our terrestrial economy is the ultimate human pursuit we are seeing heavily funded right now: longevity.
Yes, this is a massive focus.
The A16 sources featuring Dr. Andrew Scott map out a concept they call the longevity imperative.
The core premise of the imperative is that as demographic trends push average life expectancies past 100 years, we're realizing our entire societal architecture is totally inadequate. Currently, global health systems operate on a sick care model.
To put that in mechanical terms, it is like running an airline or being a mechanic, where you refuse to look at your car until the engine actually explodes on the highway, rather than just doing routine oil changes.
That is a very accurate assessment of modern reactive medicine. True healthcare, the kind required to sustain a 100-year lifespan, must be proactive, predictive, and personalized.
Like in aviation, right? They use predictive maintenance, analyzing terabytes of continuous sensor data to ground a plane and replace a part weeks before it can actually fail.
Exactly. And we are applying that exact predictive model to human biology now. By utilizing continuous data from advanced wearables, combined with AI models derived from AlphaFold predicting complex protein misfolding, the medical field can intervene decades before a disease physically manifests.
So the objective is no longer just extending lifespan, the total years a heart beats, but radically extending health span. The number of years a human is physically active and cognitively sharp.
Right. And this demographic shift is the underlying current driving global capital allocation. If you analyze the Seedscope data, you see a distinct geopolitical strategy unfolding here.
Right. The United States continues to dominate foundational AI funding and model development.
While Europe, leveraging its strict regulatory frameworks and deep pools of technical talent, is positioning itself as the leader in ethical biodata and applied medical AI.
Meanwhile, the Middle East is driving massive, sovereign, well-funded innovation, building policy-led infrastructure to transition their economies away from fossil fuels and toward high-tech data processing.
And Latin America is rapidly maturing its tech ecosystems, providing essential raw materials while moving toward major startup liquidity events.
The global economy is literally rebuilding its physical, digital, and biological infrastructure to support a longer-living, hyper-intelligent society.
It really is an incredible convergence.
We have covered a massive amount of terrain today. We examined the $6.7 trillion data center energy crunch and how that is driving AI-designed nuclear reactors. We explored the rise of AI-native teens, space-manufactured pharmaceuticals, and the longevity imperative.
All connected.
So what does this all mean? Well, whether you're building a business, investing, or just navigating your career in 2026, the premium is no longer on generating ideas. AI can do that. The premium is on judgment and execution.
Absolutely. And if I can leave you with one final thought to ponder as these technologies mature.
Go for it.
If we successfully navigate this transition, if specialized AI agents seamlessly handle our daily workflows, while advanced nuclear microreactors and 100-hour batteries provide infinite clean energy, if space-manufactured drugs allow us to live to 120 or 150, if they allow us to maintain vibrant health to 150 years old, what happens to the concept of retirement?
Oh, wow. That is a crazy thought.
Right. If an AI-native teen lives to 150, they might have 5 or 6 completely different 20-year careers. We spent all this time trying to figure out how to extend life and build artificial brains, but maybe the next great startup idea is figuring out what we're actually supposed to do with all that extra time.
We started this deep dive discussing how the invisible cloud of the 2020s is actually built on concrete, copper, and rockets today. But it turns out the most profound infrastructure we are redesigning isn't buried in a data center or floating in low Earth orbit. It is the fundamental architecture of a human life. Thanks for joining us on this deep dive, and keep questioning the future.